Hello, and welcome to the TI Precision Lab discussing op-amp bandwidth, Part 1. In this video, we'll discuss gain and how it's represented linearly and in decibels. Poles, zeros, Bode plots, cutoff frequency, and the definition of bandwidth will also be discussed. Finally, TINA TI will be used to correlate simulation results with theoretical calculations.
In this transient simulation, the OPA827 is set up in a non-inverting configuration with a closed-loop gain of 100 volts per volt. The input signal, Vin, is 2 millivolts peak to peak. The product of the input signal and closed-loop gain is 200 millivolts peak to peak. When simulated, however, the output voltage is only 154 millivolts peak to peak. Why? In order to answer this question, we need to fully understand the concept of bandwidth. First, let's review a few topics. When working with electronics, we often need to express quantities such as op-amp gain, signal-to-noise ratio, common mode rejection ratio, and power supply rejection ratio, whose values have large spans. Therefore, it is important to have a mechanism upon which we can represent a large range of values while using small numbers. This mechanism is called the decibel, or dB for short. Note that decibels have no units. This slide shows how to convert linear gain values to dB and vice versa. This equation shows how to convert from a linear gain in volts per volt to decibels. For example, let's convert the closed-loop gain of an op-amp circuit from 100 volts per volt to decibels. Substituting 100 volts per volt for the linear gain in the given equation yields 40 dB. Similarly, given a gain in decibels, we can convert it to a linear representation using this equation. While the previous example may not seem like a significant improvement in representing large numbers, let's look at the open loop gain, or AOL, of the OPA188. At 1 Hz, the open loop gain is 130 dB, which equates to a linear gain of 3,162,277 volts per volt. At 2 MHz, the open loop gain is 0 dB, which equates to a linear gain of 1 volt per volt. Ultimately, we find it's much easier to represent such a large range of values using decibels instead of volts per volt. Now let's take a look at poles and zeros. H of S represents a transfer function with 2 poles and 2 zeros. The S represents j omega, where omega is equal to 2 times pi times f. The frequencies at which each term in the numerator equals 0 are called zeros. The frequencies at which each term in the denominator equals 0 are called poles. Each pole and zero is factored to be S divided by omega plus 1. This is called the standard form because it allows you to easily determine the pole and zero by inspection. Furthermore, notice that the DC gain is factored out of the transfer function. This makes it easy to determine the low frequency gain. A plot of gain versus frequency for a pole is shown in the lower left. Notice that the gain is given as magnitude in dB. Note that the gain of a pole decreases, or rolls off, at a rate of -20 dB per decade in frequency. This makes sense because for higher frequencies, the denominator will become large, causing the magnitude to decrease. In the next slide, we will see more detail on this. A plot of gain versus frequency for a zero is shown in the lower right. A zero causes the gain to increase at a rate of +20 dB per decade in frequency. This also makes sense because for higher frequencies, the numerator will become large, causing the magnitude to increase. This slide illustrates the equations for a pole and its associated response. Later, we will provide a real-world circuit example for a pole. Looking at the equations, you can see that the first equation represents a pole as a complex number. Complex numbers have a real and imaginary part. For practical circuits, the complex function is converted to a magnitude and phase. The second equation shows the magnitude, and the third equation shows the phase. Taking 20 times the log base 10 of the magnitude gives the magnitude in dB. The graphs show the magnitude in dB as well as the phase in degrees. This type of plot is called a Bode plot. Notice that both the horizontal axis and vertical axis are logarithmic. Let's look at some key points on the Bode plot. First, the pole frequency is denoted by Fp. For frequencies below Fp, the gain is constant and is denoted by GDC. In other words, the gain at DC, or zero frequency, would be GDC. In this example, GDC equals 100 dB. Also notice that the gain at Fp is attenuated by 3 dB, or is 0.707 times the DC gain. Finally, for frequencies greater than Fp, the magnitude plot rolls off at a rate of minus 20 dB per decade. Now let's consider the graph of phase shift versus frequency. The phase shift at the pole frequency is minus 45 degrees. Phase begins to change 1 decade before the pole and stops changing 1 decade after the pole. In this region, the slope is minus 45 degrees per decade. Considering frequencies that are lower than 1 decade below the pole, the phase shift is 0 degrees. For frequencies greater than 1 decade beyond the pole, the phase shift is minus 90 degrees. Notice that Bode plots and phase plots are drawn using straight line approximations. In reality, the function will deviate from this approximation. For example, consider the points exactly 1 decade below and 1 decade above the pole on the phase curve. The straight line approximation shows the values at these points to be 0 degrees and minus 90 degrees respectively. However, the actual function deviates slightly from the straight line approximation. In practice, simulation software can be used to obtain the actual values. This slide illustrates the equations for a zero and its associated response. Looking at the equations, you can see that the first equation represents a zero as a complex number. Complex numbers have a real and imaginary part. For practical circuits, the complex function is converted to a magnitude and phase. The second equation shows the magnitude, and the third equation shows the phase. Taking 20 times the log base 10 of the magnitude function gives the magnitude in dB. The equations were used to generate the Bode plot and phase plot. Let's look at some key points on the Bode plot. First, the zero frequency is denoted Fz. For frequencies below Fz, the gain is constant and is denoted GDC. In this example, GDC equals 0 dB. Also notice that the gain at Fz is at 3 dB, or 1.414 times greater than the DC gain. Finally, for frequencies greater than Fz, the magnitude plot increases at a rate of plus 20 dB per decade. Now let's consider the graph of phase shift versus frequency. The phase shift at the zero frequency is plus 45 degrees. Phase shift begins to change 1 decade before the zero and stops changing 1 decade after the zero. In this region, the slope is plus 45 degrees per decade. Considering frequencies that are lower than 1 decade below the zero, the phase shift is 0 degrees. For frequencies greater than 1 decade beyond the zero, the phase shift is plus 90 degrees. Up to this point, we have looked at the mathematics behind the frequency response. Now we will look at connecting the mathematics to electrical circuits. First, let's consider the operation of a capacitor over frequency. It often helps to think of 3 different regions of operation. At DC, the capacitor will be viewed as an open circuit. At high frequency, or AC, the capacitor will be viewed as a short circuit. In between, the capacitor will be viewed as a frequency-controlled resistor, with a 1 divided by 2 pi Fc decrease in impedance as frequency increases. Knowing these basic relationships helps when drawing and analyzing Bode plots. Now let's look at a real-world circuit that generates a pole. This is a simple RC circuit where the output signal is measured across the capacitor. Think of it as a voltage divider. The impedance of the capacitor is given as ZC equals 1 divided by SC. The output of this circuit is given by the standard voltage divider equation, ZC divided by R plus ZC times Vin. Substituting 1 divided by SC for ZC and simplifying yields the standard equation for the pole. By inspection, you can see that the pole frequency, omega p, is 1 divided by RC. Omega p is an angular frequency, and it can be converted to hertz using the relationship omega p equals 2 times pi times fp. The final equation for frequency is given as fp equals 1 divided by 2 pi RC. Plugging in the values for this example gives a pole frequency of 159 Hz. Let's graph this function. This figure shows the Bode plot and the phase shift plot for the RC circuit. Recall that at DC, a capacitor acts like an open circuit. In this case, the entire input signal is seen across the capacitor, so the gain is 1 volt per volt, or 0 dB. Notice that the magnitude of the gain at the pole frequency is minus 3 dB. Also notice that the phase at the pole frequency is minus 45 degrees. Furthermore, the phase shift begins about 1 decade before the pole and ends about 1 decade after the pole. Furthermore, the phase shift at very low frequency is near 0 degrees, and at high frequencies, the shift is nearly 90 degrees. Finally, notice that the gain decreases at a rate of minus 20 dB per decade for frequencies above the pole frequency. This circuit is a common building block and is called a low-pass filter. The objective of this circuit is to pass low-frequency signals and stop high-frequency signals. For this reason, the pole frequency is often called the cutoff frequency and denoted by Fc. The idea is that all signals with frequency greater than the cutoff frequency are cut off or eliminated. In fact, the high-frequency signals are only attenuated and not fully eliminated. Another term associated with a low-pass filter is bandwidth. Bandwidth is simply the width of the passband, and in this case is synonymous with the cutoff frequency. In later videos, we will discuss different types of filters. For some filters, such as bandpass filters, the bandwidth definition will include both a lower and upper cutoff frequency. Ideally, we would present a simple circuit that would demonstrate a zero. However, there is no simple real-world circuit that generates a zero. The circuit presented here contains both a pole and a zero. The mathematics for deriving the transfer function and solving for the pole and zero are shown to the right. First, we start by finding the impedance of the parallel combination of R1 and C1. Next, the resistor divider relationship is used to determine the input-output relationship. Substituting the parallel impedance from above and simplifying, we get the standard form of a transfer function with poles and zeros. In this form, you can determine the DC gain, pole frequency, and zero frequency by inspection. If we plug in the values for R1, C1, and R2 into the equations, we can determine the DC gain and pole and zero frequencies for this example. Next, we will use these results to help graph this function. This slide shows the Bode plot for the example circuit. First, let's consider the gain at high frequencies and low frequencies. At low frequencies, the capacitor C1 acts like an open circuit, so you can consider this to be a simple series circuit of R1 and R2. In this case, the DC gain can be determined by using the voltage divider equation. In this example, the DC gain is minus 40 dB, or 0.01 volts per volt. At high frequencies, the capacitor, C1, acts like a short circuit. In this case, all of the signal is directed to the output, and the gain is 0 dB, or 1 volt per volt. At this point, you can finish the graph by solving for the pole and zero frequency using the equations from the previous slide. The zero frequency occurs at 160 Hz. For frequencies higher than the zero, the Bode plot will increase at plus 20 dB per decade. The pole frequency occurs at 16 kHz. The pole effectively cancels the zero at frequencies above 16 kHz. Remember that the slope of the zero is plus 20 dB per decade, and for the pole, it is minus 20 dB per decade. Let's also consider the phase shift response. Notice that the phase is at plus 45 degrees at the zero frequency. This is as expected because of our previous discussion of zeros. You will also notice that the phase approaches plus 90 degrees as expected. At this point, the phase begins to decrease at minus 45 degrees per decade because of the zero. The phase shift at the pole frequency is plus 45 degrees, which makes sense because we shifted down minus 45 degrees from plus 90. Finally, at high frequencies, the phase shifts back to 0 degrees because the pole and zero fully cancel each other. The method described here, where we consider the DC and high frequency behavior of the capacitor, is a common way of analyzing frequency response. In later presentations, we will apply this method to the analysis of amplifier frequency response. The Bode plot gives information on the gain as well as the phase shift for our circuit. In this example, we're going to calculate the peak output voltage of a 1 volt peak sinusoid at 400 Hz. Given the amplitude and frequency of the input signal, we can use the Bode plot magnitude, gain in dB, to determine the output signal amplitude. First, let's find the gain at 400 Hz. In this example, the gain is minus 8.64 dB. Convert the gain from dB to a linear representation, and then multiply the input signal by the linear gain. In this example, minus 8.64 dB translates to 0.37 volts per volt. Since the input is 1 volt peak, the output is 370 millivolts peak. Notice that the time domain simulation peak output is very close to the expected value from the Bode plot. Here we will continue the example, considering the phase shift in the time domain. Notice on the Bode phase plot that the phase shift is minus 68.3 degrees at 400 Hz. On the time domain plot, you can see that the output signal is shifted to the right in time. This is called a phase shift or time delay. The calculation at the bottom of the page illustrates how you can convert the time delay to a phase shift in degrees. In this case, the time delay is about 0.475 milliseconds, and the period of the 400 Hz input is 2.5 milliseconds. The delay in degrees is calculated by taking the ratio of the time delay to the period and multiplying by 360 degrees. As with the previous example, the time domain results compare well to the Bode plot results. Next, we will cover a step-by-step example of a SPICE AC analysis. Texas Instruments SPICE Simulator, TINA-TI, can be used to simulate the AC response, or transfer characteristic, of the circuits we have discussed so far. It can be downloaded from www.ti.com/TINA-TI. TINA-TI. Once the circuit is implemented, you can run the transfer characteristic by selecting Analysis, AC Analysis, AC Transfer Characteristic. In the AC Transfer Characteristic window, set the beginning and ending frequency as shown. Since the frequency range is generally very large, select Logarithmic for the sweep type. In the diagram section, select Amplitude and Phase. The cursors in the diagram window allow us to easily find the gain, in dB, at a particular frequency. In order to enable the cursors, simply click these buttons. Now you can either drag the cursor left and right, or you can type a particular value for X or Y. For example, typing -3 in the Y box for cursor B and pressing Enter will yield the exact cutoff frequency for this circuit. At the beginning of this presentation, we were given an OPA 827 set up in a non-inverting configuration with gain equal to 100 volts per volt or 40 dB. The input signal, Vin, was 2 millivolts peak to peak. We expected an output signal of 200 millivolts peak to peak, but observed only 154 millivolts peak to peak. Why? Looking at the transient simulation, we see that the input signal, Vin, has a period of 5 microseconds. The corresponding frequency is 1 divided by 5 microseconds, or 200 kilohertz. An AC analysis of the circuit shows that the gain is only 37.75 dB at 200 kilohertz. We originally expected it to be 40 dB. Converting the gain to a linear representation, we find it is only 77.179 volts per volt, not 100 volts per volt. Multiplying the 2 millivolt peak-to-peak signal by 77.179 volts per volt yields 154 millivolts peak-to-peak, which is consistent with our simulation. In summary, this video discussed gain and how it's represented linearly and in decibels. Poles, zeros, Bode plots, cutoff frequency, and the definition of bandwidth were also discussed. Finally, TINA-TI was used to correlate simulation results with our theoretical calculations. Thank you for your time. Please try the quiz to check your understanding of this video's content.